had a good break.
You say fatigue from squint?
Yeah. Chill out here. I'm in quantum optics now. All right, very good. So, all the notes are loaded. You know, of course, I'm sure, you know, if you want to, although I do link them on the website, the videos are on YouTube, and you know what you see. I will have to load them right away, so you can see them there. See that. There will be the next assignment. I haven't posted it yet, but it will be posted soon. Yeah.
When are we going to talk about the final part?
We'll talk about it soon. Yeah. But yeah, we'll have some time. In a few weeks, we'll talk about it. All right. So very good. So yeah, last time we started our discussion of quantum field theory, because our goal is to talk about the quantum electromagnetic field. But before we get there, setting some of the foundations in a sort of very overview, rapid fire discussion, bare bones discussion of quantum field theory. Of course, it's a very deep and complicated subject. But you know, the essence of it we can get at, and I want to, you know, that those are those, you know, critical aspects of it is what I want to focus on here in the last lecture, today and this week. So, you know, what we mean by a field is some kind of dynamical variable that's a function of space-time. Okay, so at every point in space-time, there is a value of the field. Okay, for example, in this vibrations on a string are an example of, let's say, as a function of one dimension, x. So we have one space dimension, one time dimension, and so the displacement, say, from equilibrium is the value of the field, okay? Which in this case is a scalar field. It's the field value at this big function is a scalar, okay? And in order to talk about the dynamics of it, both quantumly and classically, we want to decide what are the dynamical variables, what are the canonical coordinates, that is the canonical position and canonical momentum associated with the set of degrees of freedom that define the field. Okay. Now the field really has an uncountably infinite number of degrees of freedom because it lives on the continuum. But we often, typically, discretize that into a countable number, an infinite but countable number of degrees of freedom. And then we might take some limit if we want to think about the continuum limit. Okay? And so when we did that through a separation of variables, we were able to say the field was a superposition of normal modes, okay? And each normal mode represents a solution to the dynamics once we separate it out, the time dependence. And the amplitude of a particular normal mode is the dynamical variable, okay? And so that's our canonical coordinate. In principle, we can find, if we wanted to, and it's done in detail in the notes as an example, we can find the conjugate momentum, the canonical momentum, through the Euler-Lagrange equations by the standard way of taking the partial derivative of Lagrange in respect to the derivative, if we had chosen to do so. But I didn't go through all those details because they're not really that important for this point. Yeah?
Any reason for choosing to do it through Euler-Lagrange instead of Hamiltonian?
Because that's the definition of the canonical momentum. In order to define what the canonical momentum is, given a certain coordinate, we need to have the Lagrangian. Then there's the whole how you know, transform from Lagrangian to the Hamiltonian through whatever the hell that equation is called, with the Lagrange multipliers and all that. It's a very formal procedure, and when you do quantum field theory, that's how, when you don't know what the canonical coordinates are, that's how you do it. You have to somehow justify what the Lagrangian is. But I don't want to get bogged down in that here, because again, I really want to ultimately focus not on what's all the math that we have to do, but what does this mean, okay? Not that I'm afraid of math is not great to do it, but if we get too bogged down in it, we forget what the hell we're talking about in physics, and I don't want us to do that. All right, so the modes constitute a complete orthonormal set of functions in which any function on the space, in this case on the real line, in one dimension, can be decomposed into a superposition of that. So I should really just think about this as a Fourier decomposition. That's how I should think about what the normal mode is. The normal modes are the Fourier modes, and then there are amplitudes for each of those Fourier modes, okay? Right. So the boundary conditions will typically define what the modes are. We could think about what we call hardball boundary conditions, where the string is, say, pinned down to hard walls and has to be 0 at the walls, and that, in that case, my modes are standing waves. Right, because they have nodes and antinodes at certain positions. Or we often think about periodic boundary conditions, in which case the normal modes are traveling waves, okay? That is a way we can write down the modes, which are, say, propagating one way or another along the line. I draw this, you know, I can just think about it as a line where this point goes back to that point, right? So that's what I mean by periodic boundary conditions. And often we use periodic boundary conditions even when there ain't no boundary conditions in the real world at all, just as a way of discretizing our mode space. And then we take the limit as L goes to infinity, okay? And then it becomes a continuum. But they could actually be periodic. I mean, I could, you know, think about the modes of a string that, you know, is tied together. There could be that as well, okay? So when we did that, what we find is that the normal mode amplitudes, that is, are simple harmonic oscillators. And so the dynamics of each mode is the dynamics of a harmonic oscillator, okay? Where the amplitude of that oscillator is the amplitude of, you know, how this one mode is going up and down, or this mode is going up and down. Each mode goes up and down with a certain frequency, which is determined by the dispersion relation, okay? So given a k value, we know omega, where v is the phase velocity, okay? So in this case, for propagation on the string, okay? So what we have done is we have boiled down the dynamics of this problem to, we've separated it. It's now separable into a set of uncoupled simple harmonic oscillators. That is, you know, a standard classical mechanics problem. You start with, you know, you pluck a guitar string and you want to know how it goes. You break it down into the Fourier components, that is the normal modes. Each normal mode oscillates in time. And it's often convenient, as I'll review, because I really, really want you to have this in your mind, understand what the complex amplitude means in an oscillator, and not be afraid of that, because that, if you want to deal with harmonic oscillators, you need to work in the complex plane and understand what the heck we're talking about, okay? So we often write the solution, in this case it's a real amplitude, as the real part of a complex amplitude that goes like e to the minus I omega t, okay? And if I put that in, and generally now I just generalize to have u be either real or complex, depending upon whether I'm talking about the hard wall or the periodic boundary conditions, this is a general solution to the wave equation written in terms of a Fourier decomposition in terms of the normal modes, okay? And there's a part of it that goes like e to the minus I omega t. Because of physics conventions, that's called the positive frequency component. And its conjugate is called the negative frequency component, okay? We'll come back to this in a moment, and it's going to be a very important part of when we talk about the quantum field, okay? All right, so again, I want to review, again, the simple harmonic oscillator, because that's the whole story. The dynamics of this field boils down to the dynamics of a collection of simple harmonic oscillators, okay? At least the free field is. If we have interactions, then those oscillators are coupled in some way. But right now, this is what's called the free field, okay? So the simple harmonic oscillator, again, if I just think about the mechanical case of a mass on a spring, then I could write down Lagrangian, but I'm not. I'm going to write down the Hamiltonian already. We've gone through Lagrangian. And importantly, critically, what we said is we want to get rid of the units. And so we got rid of the units. The units are defined by the physical constants in the problem, okay? So there's only two physical constants in the problem, a mass and the spring resonance frequency, which is the square root of, you know, kappa over m, the spring constant. We have free variables, so we can't get rid of all of the constants, you have energy, position, momentum, but at least we can relate them to one another, okay? And we did that. And I really, really want you to look at that again and review that exercise. It's so important to try to understand when you're analyzing a physical problem, what are the physical scales of the problem? And what we showed in the end is that I can write this in terms of some characteristic energy scale, and then x squared plus p squared over 2, where we defined x as the dimensionless position where we had some characteristic length. The dimensionless momentum is the momentum divided by some characteristic momentum, where these three constants, the characteristic energy, length, and momentum, were related to one another. In order to make this equation. Yeah?
So I had this thought
Yeah.
last time.
Uh-huh.
If we had a Hamiltonian that had a different potential, could we do something similar, or is this specific?
Yeah, no, no matter what it is, we can think about whatever the potential is, what is some characteristic scales associated with it. It doesn't always have this nicer form. In some sense, this potential has only one, I mean, if I had a general V of Q, of course, to define what that potential is, I could write a power series in Q, but I have all of those coefficients. And so, you know, I'd have to think carefully about which of those coefficients. In some sense, this is very natural, because there's only one number that defines the whole potential, the curvature, right? And so if it was something that was not like that, it would be more complicated. Okay, excellent question, though. So with this said, we could write down the Hamilton's equations of motion and Hamilton's equation of motion that we get for the dimensionless variables, then they take a very simple form. This is basically the, that P equals mv is effectively this in dimensionless units, and the force is the gradient of the potential basically takes this form. Okay? When we made it in dimensionless units, it has that form, and the solution to this equation, say for the position in dimensionless variables as a function of time, is this. Okay? So it takes this really beautiful, everything had, all the units are gone, it just looks so nice and symmetric. Okay? Yeah?
That P dot is the one with the bar under, is it supposed to be?
Big P,
Yeah, sorry. That's, I will be sloppy because I will be. Yeah, but yes, thanks for asking. Everything here is dimensionless. So this is the form which we said, importantly, the canonical position momentum are, for the point of view of a harmonic oscillator, are what we call the quadratures. Okay? They're called the quadratures because any function which oscillates at a single frequency, omega, can be always written as some amount of cosine and some amount of sine. And those two functions oscillate 90 degrees at a phase with one another, so they are in quadrature. That's where the term quadrature comes from. And it is convenient and very useful to rewrite this as the real part of everyone see that? Because the real part, this is a real number, this is a real number. So the real part of this is cosine, and the real part of I times that is sine. So we see that we can write the solution as the real part of a complex number which has a real and imaginary part, or equivalently an amplitude and a phase, right? Where A is the amplitude in polar form, that's the amplitude, and the phase is the arctan of the real over the imaginary part, right? Just from a complex number. Yeah?
And this expression, is it still tied to the mass on the spring, or is this completely general for any oscillating function?
It's true for any oscillating function, and that's important. Any function, at this point, the physics of this is gone. It's just something, it satisfied the differential. In fact, each one of these guys, if I take the second derivative of it, it's easy to decouple these equations. Both x and p are solutions to the simple harmonic oscillator equation, okay? So anything that satisfies these equations this will be the solution, okay? Depending on the initial conditions come from x at 0 and x dot at 0, and they satisfy these things. So the mechanical oscillation is going to be generalized to the oscillation of something that is so abstract, the electromagnetic field, which is not a mechanical oscillation of the ether, as of course people thought to be true in the 19th century. But anything, we'll talk about the quadratures of the field, the electromagnetic field, in a moment, okay? Good, right, so we have amplitude and phase. and we have quadratures. Those are two ways of thinking about the dynamical variable for a single oscillator. And when we put this in to the solution, of course, energy is conserved, so the energy is the same at all times. Oh, by the way, I guess I should say that we define alpha as the complex amplitude, but with this horrible factor of square root of 2 that we just have to deal with. And that's just because I chose, oops, this is wrong. Okay, let's go back. That's just because I choose, and now I get it right, to not include the 2's in the, I could have absorbed the 2's into the definitions of the, I mean, there's no, for sure, this is what, that you define what the characteristic scales are, and that's just, so now the 2 is left over here. We could have gotten rid of that 2 by putting it in here, but I chose not to because it means other things are much easier, okay? In some of the, especially in the older literatures in the 1980s, people did it that way, and it's just so confusing. You'll see, I'll explain to you why, where that is. Okay, so with this said, I should say that if I look at, x is the real part of this times root 2, and p is the square root of 2 times the imaginary part. So we have this horrible factor of square root of 2 that we have to keep around and remember. Okay, that's life. Yeah, boo.
Make us like
Yeah, boo.
Which one
Okay.
of the alphas then, like the A we have?
Yeah, exactly. So let's see. So alpha of t here, in this case, is equal to alpha at 0. Okay, well, let me say it this way. What's the equation of motion for the complex amplitude? Okay, this is what we call the complex amplitude. Also known as a phasor. Okay. Well, that's x dot plus I p dot over root 2, and if you put that in, you get this. It's easy enough. Put it in, check it. Okay. So alpha dot is so what is the solution to this differential equation?
12.
No.
1.
No. Let's try harder. It is. So in particular, what exactly is it? Alpha of t equals
E negative I omega
t, but what about,
with complex issues.
and what's the initial, which is, this only depends on one, so that's the solution. Okay? Which is this. Okay? So if I multiply this whole thing by square root of 2, this is equal to the square root of 2 times alpha of t. Okay? So alpha at time t equals 0 is a e to the I5 over root 2. Yeah. Did you have a question?
I guess, are we in, like, would we consider that alpha to be just our function in phase space then?
It is, so they're the same thing. So that's exactly right, Tristan. And so we have two ways of thinking about describing the dynamics. I can think about this as phase space, or I can think about it as the complex alpha plane. They're one and the same. They are one and the same. Up to a factor of root 2 because that's the way it is, okay? So this is not the real axis, it's square root of 2 times the real axis, or the other way around. So yes, it's square root of 2 times the real axis, and this is square root of 2 times the imaginary axis. Okay? So if I think about this in terms of real alpha and let me just write this. I'll leave it here. I want to say one more thing before I draw this phase space, which is, what is the energy as a function of time? If I start with some initial condition, I have some initial position, some initial momentum. What is the energy as a function of time?
Okay.
No damping, just for the harmonic oscillator.
What's the magnitude?
So yeah, we're getting close.
Should be constant.
Firstly, it's a constant. The energy is the energy at all times, but the energy as a function of time is this, right? And so the energy as a function of time is this x squared of t plus p squared of t. But that's just the amplitude squared over 2. Right? Because the amplitude, x squared plus p squared, is the amplitude, and the amplitude is the same at all times. So the energy is proportional to the square of the amplitude, and without damping, that's conserved. And in terms of these variables, with that square root of 2, that's the magnitude of alpha squared, right? Because that's square root of 2. Or I can write it as alpha star alpha, which of course is the same at all times. Right? If I multiply that, this is, yeah. Yes, Ben?
So you sort of equated the in phase and in quadrature x and p to a e to the I v over there, I believe. You're saying those are this.
This is the phasor at time equals 0, which is here.
Right. I'm trying to relate it to a here. Is there
A is the amplitude
at t equals 0?
at all times, because the amplitude, what changes is the phase, but the length of that vector is the same. So the complex number, so the solution to this problem, alpha's function of time, is alpha at 0 e to the minus I omega t. A at 0, alpha at 0 is 1 over 2 times A e to the I phi, all right, which is equal to so this is the complex amplitude as a function of time. It has the same magnitude, but its phase is changing. And its phase is changing exactly like this. It's going around this way. At time t equals 0, this is the phase. At a later time, this is the phase, which is equal to that from this axis, that minus I omega t, okay? And it goes this way, because if I pull the spring and it starts this way, it goes backwards, and its momentum is in the negative. So that's the direction, that's why it's e to the minus omega t, because that's the way the phase goes. It goes that way, okay? So this is the complex amplitude, and x, which is the square root of 2 times the real part of this, is a cos omega t minus phi. Ta-da, that's the solution, which is what we said before. So I can think about the motion here of the oscillator in phase space as equivalently the motion of a complex phasor in complex phasor space. They are one and the same thing up to this horrible factor of square root of 2, okay? And the energy is the square of the amplitude with some constants. And this amplitude there is the length of that vector. So in dimensionless variables, this is going around in a circle. That is the trajectory of a harmonic oscillator. Yes?
Is uncertainty associated with these quadratures?
It is, so we're about to do that.
Okay.
Right now, everything is classical. Now let's make it quantum again. So we did all this last time, but it's so important. I wanted to just do it all again because this is, you gotta get this stuff really, really solid in your minds. Okay? So as we were just saying, so now when we have quantum, life is good because there's a new constant in the world, h bar, and for you, Benny, that's action. So there is going to be action in the world. And action is position times momentum, right? So that's gives us now the characteristic units. So my characteristic momentum now is the square root of m h bar omega, and my characteristic length scale is equal to whatever the heck we got there, h bar over m omega. Okay? And our characteristic energy scale, thus, from what we just said, is what we would expect, h bar omega. So we now have from the mass, the resonance frequency, and h bar, what the characteristic length, momentum, and energy is in the problem. And the Hamiltonian now is an operator, so we have the, so this is the Hamiltonian of the simple harmonic oscillator written in dimensionless units. Yes?
Should the x be squared?
It should be. Thank you. So, importantly, because now we have that the position of momenta don't commute, in dimensionless variables, this says that x and p, they don't commute in this dimensionless way in terms of I. We've got rid of the h bar because dimensionless length times momentum bar, or q. But I'm sorry, I'm going back and forth. Okay? Moreover, we can define the quantized version of the complex amplitude. This operator is not Hermitian. Okay? It's not equal to its Hermitian conjugate. The Hermitian conjugate is x minus it over root 2. Okay? So this is the quantized version of the complex amplitude. And based on the canonical commutation relations, this tells me that the commutator of A with A dagger is 1. That's why we don't absorb the root 2 into the thing. Otherwise, we'd have a half in these commutators, which sucks. You do not want to have A with A dagger commuting to a half. Although, you know, people did that, and I know Jared Milburn, you're a great guy, but that was just the wrong way to do it. Okay, so, and this was the wrong word to use, but whatever. All right, so, very good. So, with that, what we have is that the Hamiltonian, when we substitute in this, is equal to h bar omega over 2 A dagger A plus A dagger over 2. Okay, so the Hamiltonian quantumly, remember classically somewhere, where did I write it down? On the other board now.
You have it there, right?
Oh, here it is. Was alpha star alpha. Now it's symmetrized because we don't know which order, but that comes out naturally, okay, when you put that in. And if you use this commutator, what it tells us is that the Hamiltonian has this form for the simple harmonic oscillator, which everyone knows. Where this operator here is defined as the number operator. And it's called the number operator because the eigenvectors of that operator has eigenvalues that are the natural numbers, the non-negative integers, okay? So that means that the energy eigenvectors are the number states with eigenvalues n plus a half times h bar omega. Yes?
Should I think of these numbers as sort of the modes of the oscillator?
Oh, well, we're going to say more about that. I mean, right now, we're talking about one mode,
Okay.
okay? One mode that has one frequency omega. So they're not different modes, they're one mode. I'll come back to the modes in a moment, but let's just focus for the right now on just the motion of a particle in a harmonic well and its energy exit. Then we'll come back to the mode problem in just a moment.
Thank you.
So again, if we think about this as a in wave mechanics kind of picture, here's the potential as a function of position or x. And we have these energy levels, right, associated with n equals 0, 1, 2, 3, with an equal spacing for a harmonic oscillator, each spaced by energy h bar omega. What n represents here is number of quanta of energy in the motion. That's what n is. The number of quanta of energy in the motion. We can have a situation where we have no quanta. That's the ground state. The lowest energy state has no quanta. N equals 0. Now, of course, you remember that even when that's true, there is finite energy in the system. In fact, we have here 1/2 h bar omega, which is called the 0 point energy. Okay, so even when we have no quanta of excitation, we have some energy in the system, right? I want to just remind, so again, if I can rewrite this b sub n as n times h bar omega plus h bar omega over 2, okay? How should I think about this? Well, this is the generalization kind of, remember the energy we said for the classical oscillator was like the square of the amplitude. What this is saying is the number of quanta is like the square of the amplitude. It is A dagger A. A dagger A is the square of the amplitude. The number is the square of the amplitude. However, quantumly, the amplitude can't be any old thing. The amplitudes are quantized. So I can't have any old amplitude. The amplitude has to be in quanta of h bar omega. Now, we're going to see there's a fuzziness about this. Let's come back. Really, I shouldn't think about this on a definite line, but with some fuzziness associated with it, quantum fuzziness. Why? Well, that's associated with what is certain and what is uncertain in the problem, okay? So these are energy eigenstates. The energy eigenstates are like having certain definite square of the amplitude in the problem. But what about the position and momentum? How well defined is that when the particle is in one of these energy eigenstates? Okay. Let's just start with the ground state. That's the lower to n equals 0. What is the mean position? How would you calculate that? Oh, before I do that, I guess I should remind you of some properties. These complex amplitudes are also the ladder operators. That is to say, they raise and lower through the harmonic ladder.
Similarly to how we have A and A dagger and X and P, we can rearrange it so we get X and P in terms of A and A.
That's right. That's what we're going to do. So let's just first remind everyone and ourselves what the action is of A on one of the number states. This is the lowering operator. It brings me down to n minus 1, but with a prefactor, because this is not a unitary operator, it changes the norm of the vector. And A dagger on this is the square root of n plus 1, times n minus 1. A on the vacuum is 0, it annihilates.
You mean state n plus 1, right?
Right? So, okay, so now we come to the point, which is, if I write, I want to calculate the expectation value of x in what is that for the ground state? How would I calculate it?
You relate that to the A and A dash.
Right, in terms of A and A dagger. Which is 0. Why? Because A dagger makes this 1, but 1 is orthogonal to 0, and this annihilates it, or vice versa. So this is 0. The same thing easily for P. All right. So the mean position of the ground state is 0. That's kind of what we expect. What about the fluctuations? So the uncertainty is, which is the variance of the uncertainty, is this. And so for the ground state, what is x squared? Well, again, I do the same thing. I plug in terms of A and A dagger, and I get a half A squared plus A dagger squared plus A dagger A plus A dagger. Yes?
Just to confirm, that's delta x all squared?
Yeah,
No, I think it's still
Delta x squared is the mean of x squared.
he's asking if there should be parentheses around the delta x, so that
Oh, this thing is squared. Is that what the question
on the
is?
left-hand side.
Yeah.
Delta x is one variable.
Yeah.
Yeah.
Yes, this is the variance. We always write it this way. I don't know where the project that way. There's no, we never write it. At least I never write it with parentheses. That is the variance. Like when I write sigma squared, that's the variance. Okay. So with that said, what is this? How do you calculate it? You use count, okay. So firstly, whenever I have the expectation value of something like this between number states, I have to have the expectation value have the equal number of A's and A daggers in it. Otherwise, it's going to be orthogonal, right? So this has more A's than A daggers. This has more than A daggers, so A daggers and A, so I can forget about it, right? You can quickly see that. This one is the number operator acting on that, which on the vacuum is 0. So the only thing that's non-zero is this. And so as Andrew was saying, what I want to do is I want to use the commutators to get all the annihilation operators on that side to annihilate this. So it looks like the number operator, because I know what the number operator does. So to do that, I write this as A dagger A plus the commutator, which is 1. Okay, everyone see that? And so what is the answer to this whole thing?
Or 1/2.
1/2. And because it's symmetric in X and P, it's also true for P squared. Okay. So what we have found that for the ground state, delta X, which is the square root of that, is equal to the uncertainty in P, which is 1 over root 2 for the ground state of the harmonic oscillator, which says that delta X times delta P is equal to 1/2, which is the minimum possible, according to the uncertainty principle. So the ground state is a minimum uncertainty state.
Where did we set H bar to 1?
I got rid of it long ago.
We've been using units.
And these are X and P in dimensionless units.
Okay, yeah.
So when I'm always talking about X and P in dimensionless units. At this point, it's not like I said H bar to 1. I did not.
Yeah.
I want to just make that comparison. I'm writing X, the whatever X is in the characteristic units. Okay, so the actual, it's a very good question. What is the uncertainty in real units? Well, it's the characteristic over root 2, which is the square root of H bar O to M omega. So that's the 0-point fluctuations of the ground state So we now see what the characteristic length scale was. The characteristic length scale is basically the 0-point length scale of the ground state. That's what it is, up to a factor of square root 2. Okay, so we could have guessed that, maybe, if we, in hindsight, with retrodiction and knowing something from the future, but that's what comes out. Okay, and similarly, the uncertainty in real units here is that, and thus delta X. Now we're happy that's the minimum uncertainty state. Okay, very good. I challenge you with a little bit of work to do this to ask what is the uncertainty in position for a given number state. Again, because everything is symmetric in X and P, when I'm looking at an energy eigenstate, this is equal to n plus 1/2. Okay, so the fluctuation in X and P, if I'm in the nth energy eigenstate, is equal to n plus 1/2, which is greater than 1/2. It's only a minimum uncertainty state for the ground state. So all of these things have uncertain position and uncertain motion. That is to say, there are uncertainties in the quadratures. If I'm in the ground state, I have the minimum uncertainty product, but in other states, I have higher fluctuations in this. Okay, I should remind you about, so the energy eigenstates, the number eigenstates are not position eigenstates, nor momentum eigenstates. There's uncertainty. I can ask, what is the probability distribution or probability density to find some position or some momentum? That's given by the wave function, which is the position representation, say, of the nth energy eigenstate. Which is what? What is the wave function? What are the eigenfunctions of the simple harmonic oscillator? They're Gaussian-esque. Close, yeah, maybe.
Gaussian with Bessel stuff.
Close. There's one of those other guys. Hermite polynomial.
Oh, I forgot to draw it.
Yeah. So this is equal to, there's some amplitude, e to the minus x squared over n plus a half times 2 times a Hermite polynomial, the nth order Hermite polynomial as a function of x. This is a Gaussian, oh no, this guy, no, that's not correct. The Hermite polynomials like this. And it's, you know, factor of, yeah. Okay, so for the ground state, the Hermite polynomial is a constant, and the ground state is just a Gaussian, but then I have this Hermite polynomial here. And the momentum space wave function is the same, because everything is symmetric except it has a factor of I. Okay, very good. All right, let's come back now to say what this means for the quantum field. Okay. So now I'm going to replace these guys. There's some characteristic scale, I'm not even going to worry what it is, times my complex amplitude now becomes the annihilation operator. And in the other case, some characteristic scale here, I've not written the units, a dagger. This is my quantum field.
Should our u of kx, should that x be an operator now?
No, that's an interesting point. Space-time is not quantized. We don't have a quantum theory of gravity. Space-time is a classical variable. So if you saw the colloquium, when was it? The week right before, and I highly encourage watching it. I don't know if it's recorded, because it's amazing. You know, there's a problem. We treat space-time as, so space gets demoted, you know, in quantum field theory. Remember, and I'll come back to some of these issues, it's very complicated. But in standard quantum, non-relativistic quantum mechanics that you learn at the beginning for a particle like an electron, its position is a quantum variable, but time is not. Time is, and when you go to quantum field theory, it's not that time gets promoted, space gets demoted. No, it's a problem. Okay, we'll come back to some of this. Okay, so again, this was our Fourier decomposition that we had classically. The role now, what were the amplitudes, the complex amplitudes of the Fourier modes are now quantum operators, okay? And so this is the quantum field operator. This is in the Heisenberg picture as I've written it. Because my operator, my field operator is a function of time. I could write it in the Schrodinger picture as well with, you know, some characteristic scale, A, K, UK, plus Hermitian conjugate. When I write this in the Heisenberg picture, I'm making these guys functions of time. And they evolve as a time according to the Heisenberg equations of motion, and their solutions are exactly the classical solutions. Okay? All right, now I want to think about the physics. We've got so much going on here. So how should I think about what's going on physically? What is the quantum field? How should I think about it? Well, before I do that, I want to ask, we talked about the operator. What is the Hilbert space? Operators act on Hilbert space. What is the Hilbert space that is associated with this quantum field?
Space of all ends and states.
Close. So if we had a single mode, that is the Hilbert space, which is for one harmonic oscillator. But each mode is its own harmonic oscillator. So the Hilbert space is the tensor product of every degree of freedom. So I have mode K1, mode K2, dot, 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 you know. And each one of these Hilbert spaces is the Hilbert space of a harmonic oscillator, which is the Hilbert space that are all square normalizable functions on the line. So these are simple harmonic oscillator Hilbert space, which is the same Hilbert space of any, they're spanned by the number states. The number states of a given mode are spanned, that Hilbert space for that mode. So now I ask you, what is an example of a basis for this Hilbert space? By the way, this Hilbert space is known as Fock space. And states within are known as Fock states. Although we often talk about Fock states as only a particular basis states, but that's wrong, but that's just the way it goes.
This is an infinite dimensional Hilbert space.
It's, each one of these are infinite dimensional. So I again, what is an example of a basis for the Fock space? Yeah, Andy.
It's like the occupation basis, how many, if each Hilbert space has how many particles?
Exact, or how, well, this is exactly right. In this case, if I think about it as a bunch of, each harmonic oscillator is spanned by the number spaces. So the whole Hilbert space is the tensor product of the number bases for each state, right? So a basis I would write as the number of quanta of excitation in mode 1, the number of quanta of excitation in mode 2, the number of quantum of excitation in mode 3, whatever the kth mode has that, dot, dot, dot. Okay? So that is a basis. Each one of these, and each one of these goes from 0 to infinity. It tells me how many quanta of excitation I have in that mode. Often we don't write the tensor product, we'll just write it as n1, n2, dot, 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 nk, dot, dot, dot. Yes, Ben?
So if I were thinking about photons, would an app basis just be the states which trigger N1, N2 clicks on the SPD?
Yeah, we'll get to photons soon. We'll get there soon, but yes. Well, hold those thoughts for a little bit. Yes.
Are we at uncountable basis states?
No, they're countable. 1, 2. So yes, we can, but it's infinite. It's infinite. Now there are two different kinds of bases here, right? I mean, there was the basis of in Hilbert space, number of excitations, versus what I said here about this being a function space, right? We took space-time and we broke it up into a countably infinite number of functions through our mode decomposition. But that's not the Hilbert space, that's not the vector space we're talking about. They're interrelated and it's confusing, and I'll try to emphasize those points. Yes?
When you say that N1 can be 0, 1 to infinity, it can actually be a superposition of those two, right?
Well, right now, the basis, no. This is the basis.
The basis can't.
This is the basis. We'll talk about superposition in a moment, but these are the basis states. And the basis states are labeled with numbers that range from 0, they're the integers that range from 0 to infinity. These are the basis states. Now, you are absolutely right. I can talk about an arbitrary state in the Hilbert space, which in principle can be a superposition sum over all the n's. All the n's have to go from 0 to infinity. C n1, n2, ... So this is a more general state in the Hilbert space, but this is a basis. And I could have superpositions of that. Okay? Yes, Leroy.
Is the right way to look at it that you have like a bunch of different independent harmonic oscillators?
Yep,
That each have a different frequency?
that's
and
right.
you're creating a mode at each frequency.
That's exactly right. So we've broken up the field into a bunch of harmonic oscillators. Those harmonic oscillators are the normal modes, and they each oscillate at their own frequency, given by this. And each one, the amplitude of that is not the position of any one mass in the string, but the whole collective mass of the spring. And I've separated into uncoupled set of oscillators, each one having their own independent frequency, and each harmonic oscillator is described this way, okay? Now, I want to go to a point that Andy snuck in, which he mentioned the word particle. And so now we're coming to the whole question of particles and fields. So let's say I had an example of, I had a state where I created one quantum of excitation by writing the creation operator that way, okay? So that has one quantum of excitation in mode 1, say, in the case of this, say, this is the first mode. Okay, so one quantum of excitation in that mode. I'll write that as 1 in mode K1. Okay? These are all the same, different notations for the same thing. I have one quantum of excitation. What we would say is one quantum of excitation one phonon. So this is the excitation we're talking about, are the vibrations of the spring. We have one phonon. That phonon is what we call a particle. What a particle is a quantum of excitation of the field. In this case, it's not a fundamental particle like an electron or a neutrino or a photon. it's what we call a quasi-particle, because it's related to the collective motion of things, but that's irrelevant. What's important is that what makes it a particle is that it is indivisible. I cannot break it into different pieces. It's one particle under Dirac with the Schrödinger equation and quantum mechanics for all. Okay? And so that's what we mean by a particle. Okay? Now, when we think about, so, again, this goes to some degree to Tristan's question about superposition. I could put, so one particle in this mode I can think about the particle as this being the wave function of the phonon. I have one phonon, it's a particle, and it's in the mode, which means that's its wave function. I don't know where it is. I've just solved the problem of a particle in a box. And if I had the particle in the box and ask, what is the ground state? Well, here it is. Okay. Now, I could have a particle, I can think about this state. So that's a state by the way, when I write 0 like this is a shorthand for 0, 0, 0, 0. Okay? We'll come back to that in a moment. That's the ground state of the field. How should I think about that state? Firstly, I ask you the following question. How many phonons are there in the mode? Or in the field? This is multiple modes. I'm summing over the modes. K is the mode index. How many particles do I have? Do I have a definite number of particles or an uncertain number of particles? Yes, Nate?
It would be the number of modes you have, but isn't that infinite?
It's not quite. So the total number operator is the sum of the number in every mode. That's the total number of particles. So, first question I have for you, is this state an eigenstate of the total number operator, or are there an uncertain number of particles?
Uncertain number.
Uncertain. Why do you say that?
Because it sounded better.
Because there's a superposition there, but no. Every one of these states has how many phonons? 1. Now, the amplitude to be in that is CK, but every state has exactly 1 phonon. I don't know which mode it's in. It could be in this mode, it could be in that mode, it could be in that mode, but it's 1 phonon. Its mode is uncertain, but it's got a definite, this is a 1 phonon state. I don't have to be in a normal mode to have exactly 1 particle. It could be this. This is a wave packet. This is a single phonon wave packet. Okay, it's a single photon wave packet. In fact, I can think about, so let's think about wave packets in ordinary quantum mechanics. I can think about K as plane waves, right? Which have wave functions. So these are my momentum eigenstates. These are the kets. This is its wave function. This is one particle, like the way we solve an electron, a free particle. You with me? If I wanted to, I can think about a wave packet as a superposition of Fourier components, which has a wave function it's one particle, but that particle is not an indefinite momentum eigenstate. That's exactly what this is. This is one phonon. I can think about the K's like they have a definite momentum, but I have a superposition of different K's. So this is a one phonon wave packet, okay? This is what we call the second quantization. It's called second quantization because I kind of turned the wave function into an operator, right? This was the wave function of the particle in the box, and this was its amplitude, and I put a hat on it. So this whole formalism is what we call second quantization, which we'll talk a little bit more next time, given the time that we have. So I can have a system which has one particle. That one particle can be in a normal mode, or it could be a superposition of normal modes. It doesn't have to be a basis state. It could be a superposition of the basis states. But I can have a superposition of basis states, all of which have the same number of excitations, or some of which have different excitations. So one as well. I wanted to say one word about the ground state. That is what we call the vacuum. It's the lowest energy state of the field. How many quanta of excitation are there in the vacuum? 0. There ain't no quanta. Nonetheless, that doesn't mean everything is 0. Okay? Firstly, I ask, what is I'll call this, so this we'll call 0. What is the mean field? What is the value of the field at any time? How would I calculate it? Well, I plug that in, right? Everyone with me? And what is that?
0.
0. There is the mean field is 0 in the vacuum. But what is this? It's not 0. For exactly the same reason that we did when we thought about the single oscillator, and I asked what is the position of the oscillator in the ground state. On average it's 0, but it has 0-point fluctuations. So even in the vacuum, the fact that there is an uncertain value of it, even though the expected value, the mean value of the field is 0, there are fluctuations around the mean. This is what we call vacuum fluctuations. Meaning if we were to somehow be able to do a measurement of the value of the field at any time, and we wouldn't get a definite answer. It would be a different answer at different times, okay? What about the energy of the system? Well, the Hamiltonian of the system is the sum over all the modes, the Hamiltonian for every mode, which is equal to n plus a half h bar meter, where n sub k is a dagger a for that mode. Right, everyone with me? This is what it was for one mode, but we have all the modes. So every mode is a harmonic oscillator, and every mode, that's the Hamiltonian for it. Okay. What is the average energy?
For zero is some of the points.
Which is, these things go into, which is infinity.
Well, that's weird.
Meh. You know, there are all kinds of infinities in quantum field theory. The 0-point energy of the field, at least this field alone, is infinity. Now, we really generally don't care, because what the energy of the ground state is does not affect anything that is measurable. We only see the relative energies. The dynamics only depend on what is the energy differences. So typically in quantum optics, we just ignore this, and we write this as h bar omega k a dagger a, and forget about, that's an overall energy. It gives me an overall phase of the wave function, and it doesn't really matter, except in general relativity. Because in GR, the metric, the curvature of space-time depends on the local energy density. And if there is energy density in the 0-point motion, that should absolutely contribute to, and that might be a component of so-called dark energy. The cosmological constant should for sure have a component. The problem is that if you do quantum field theory, it doesn't work at all. Now, it turns out, and I think we noticed recently, that fermions actually contribute to negative energy. It's one of the reasons people like supersymmetry, because if we had a supersymmetric particle, if every boson had a supersymmetric fermion, then it would totally cancel the 0-point energy, and everyone would be happy, but we've never found the supersymmetric particle. So it's a really interesting problem, but I think Donald mentioned the Casimir effect, which we might talk about. We can look at the relative 0-point fluctuations by the boundary conditions, because the boundary conditions determine the number of modes. So if you change the number of modes, you change the different 0-point contributions of the system. Yes?
So removing the 1/2 doesn't remove the problem of infinity. You just don't care about the 0-point fluctuations.
It doesn't remove the problem of GR.
The
fact that this is infinity doesn't remove it. We're just looking at, from now on, we think about the energies relative to the ground state. The fact that the ground state has infinite energy, I'll just walk around like this and say, I don't really know what to say. Yeah.
So is that assuming an infinite mode?
It does, yeah, it does, it does. I mean, if there is something that were cut off at the Planck scale or something, then yeah, it's true. But even then, it would be a very large number. Okay, we'll talk more about this. I would encourage you to read the notes. We're going to think about this very complicated problem. We talked about the ground state. We talked about a little bit the case where we had exactly one particle. what if we have two? And we'll talk a little bit more about that. And the whole story about second quantization, identical particles and bosons. Okay, that's coming up, and we'll quantize the electromagnetic field on Thursday.
What are these,